Okay. So in the earlier lectures, we discussed the transmission interconnection. That is why we need to do the transmission interconnection. Obviously, the basic objective is to operate the power system economically and reliably. Reliably means to maintain the continuity of supply. Then we studied flow of power in AC transmission systems. In that, we discuss power flow in parallel transmission lines, uh, as well as power flow in mesh transmission system. With some suitable example, we have been discussed that, and we found the opportunity for flexible AC transmission system controllers in order to regulate the power flows through the transmission lines such that no line will be get overload, and by that mean we operate the transmission line economically. Now we will see the next point, that is what limits the loading capability. If we consider a particular transmission line, if we consider a particular transmission line, so what are the ratings of that transmission line, and based on that, or based on what parameters that particular ratings of the transmission lines has been decided, and how actually we operate the transmission line by keeping in mind that limitations in mind. If we consider one particular transmission line, then the power handling capacity of that particular transmission line means that is utilized, or that is help us to uh, actually load that transmission line according to system requirement. So the factors which limits the power handling capacity of the transmission lines are like thermal rating, dielectric rating, and stability limitations. Thermal rating means we can say the electrical power rating of a transmission line. Why it is called as thermal rating? Because the electrical power which is handled by the transmission line is decided by how much current rating it is having and how much operating voltage rating it is having. When we say the transmission line is having some ACSR conductor, so the material of the conductor is suppose silver, we can say aluminum, and the size of the conductor, according to that, it offer some resistance. That is R is equal to rho into L by A. That is rho is the resistivity of the material, L is the length of that total transmission line conductor, and A is the cross sectional area of the conductor. According to that resistance, whatever maximum current we can allow to pass through that conductor, so that whatever copper loss going to take place, that is I square R loss going to take place, will hit the conductor, because that copper losses are going to be converted in the form of an heat, and that heat is over the conductor. Now whatever that heat will be there, it will be such that it will be thermally sustained by that conductor, means that conductor should not break. On the basis of this, that current rating of that conductor has been decided. Obviously there are some standards. Let's say for an example, in our house wiring, when we talk about wire of 1 square mm, 1.5 square mm, 2.5 square mm, 4 square mm, and according to the circuit of that house wiring, for a particular tube light or fan, we use either 1 square mm wire or 1.5 square mm wire. That 1 square mm wire is having an current rating of, let's say, 5 ampere. 1.5 square mm wire is having a current rating of 7.5 ampere. Similarly, 2.5 square mm wire is having a current rating of 10 ampere. 4 square mm wire having a current rating of 15 ampere. So according to that circuit, where that light fans are all fed through 1.5 or 1 square mm wire from the switchboard, but where the wire which is carrying all current to that switchboard, all devices, let's say 2 3 fans or 2 3 tube lights are there on that switchboard along with some socket in order to connect 5 ampere load or 15 ampere load. So according to that, that main wire coming to that switchboard will be of some 4 square mm or 2.5 square mm. So that is the algebraic summation of total current which is going to delivered by that switchboard. Similar to that, for overhead transmission line, whatever conductor we are using for transferring the power, so how much power we want to transfer. So for that power and at what voltage level that power we are transferring. Let's say it is a 400 kV transmission line or 220 kV or 132 kV. So according to that voltage and the power which we want to transfer at that voltage, the current has been estimated, and based on that current, that conductor configuration, material, its cross-sectional area has been decided. So for a given transmission line, according to that current rating and the operating voltage level rating, it is having some power handling capacity, and that capacity is called as the thermal rating of a transmission line. Obviously, the rated voltage and the rated current of that transmission line. So that is basically depends upon the physical parameters of that transmission line, like as I said, the type of conductor, size of conductor, then ambient temperature, wind condition, your spacing between the conductor, height above the ground, that is we can call it as a ground clearance. So these all factors are going to decide at what actual current that transmission line can be operated. And based on that, the actual power or thermal rating of that line has been decided. Out of these physical parameters, some parameters are varying. Let's say ambient temperature is varying seasonally. In winter, it is low. In summer, it is high. So according to that, the current handling capacity of that conductor is also seasonal, we can say, varying. So because of that, the given transmission line may have a 2 3 thermal ratings. According to that ambient condition, that line may be loaded having a thermal rating of 1000 megawatt or maybe 800 megawatt or 900 megawatt if the atmospheric condition is varying accordingly. So in view of actual loading the transmission line, there are some real-time computers used to estimate the thermal rating of the line, and according to that, that lines can be loaded up to that only in order to avoid the further inconveniences or further transients, we can say. These thermal ratings are varying by the factor 2 to 1. As I said, 1000 megawatt, if it is in the winter season, maybe having an capacity to carry the power up to 500, 600 megawatt only in the summer region if the ambient conditions are very worst. So while loading the transmission line, it has been taken care that it has to load below its thermal rating. Second one, that is dielectric limitation. Just just minute. Second one is the dielectric rating. As I said, thermal rating is the related to current rating of a conductor. So similarly, dielectric rating is the voltage rating of the conductor, and that is decided by spacing between the conductor, ground clearance, and so on, as well as the ambient conditions. Any transmission line designed for a particular operating voltage rating has an acceptable variation of plus minus 10%. Means if 400 kV transmission line is there, then that can be operated in the range of 360 kV to 440 kV. And obviously, when it is operated for higher voltage rating, then according to that, it is having an higher power carrying capacity for that higher operated voltage. So this loading of a line should be such that the voltage variation should be within the acceptable permissible limits. And according to that only we can load the transmission line. Obviously, whatever voltage variation we are talking about, that is not under steady state condition. Means if any sort of transient takes place, let's say some fault happens or some suddenly drop in load takes place. So under that circumstances, whatever rise in voltage should will be takes place. That should be such that it should not puncture the dielectric material between the conductors or between the ground clearance. The spark should not be takes place under that transient condition. So by taking care of this all, accordingly the transmission lines has been loaded. Means obviously there are some protection against such conditions, like in order to avoid the over voltage, protection against over voltage, we use some arresters, that is metal oxide arrestor or some surge diverters that you already studied in switchgear and protections. So that is the second factor which limits the loading of the transmission line. And third one is the stability. As you all know, stability is nothing but the ability of the system to remain in synchronism. As the power system having and many more generating stations along with different loads at different buses. So there is always an variation in the load on the power system according to your timing of operation, people utilizing that energy. So that variation in the load has been regulated by the generators automatically such that all generators along with loads are in synchronism. Means they should not lose the synchronism. Means the system should not become unstable. So stability can be assessed in a many ways. There are many definitions, many terms used for analyzing the stability of the given power system, like steady state stability, dynamic stability, transient stability, frequency collapse, voltage collapse, then your subsynchronous resonance. So here as an introduction, we should be aware about the difference between these terms. The first term, that is steady state stability. That steady state stability is nothing but the ability of the power system to remain in synchronism for small changes in the load. That is what the actual operation of the normal operation of the power system. Because in under normal operating condition, there is always a small changes in the load happens on the in the power system, and according to that, that power system has to regulate that. So the ability of the system to remain in synchronism, the ability of the power system to remain in synchronism under small variation in the load condition, that is called as the steady state stability. Transient stability is nothing but the ability of the power system to remain in synchronism after sustaining a large disturbance. And that large disturbance may be your fault, maybe sudden loss of load, sudden loss of generation, sudden loss of electrical network, that is transmission line, one of the transmission line or two of the transmission line of given electrical network. So that create an large mismatch between the generation and demand, and the system which maintains synchronism under that condition, that is called as transient stability. Obviously, steady state stability limit is greater than the transient stability limit, because for small variation in the load, if you want to regulate it, a small margin is required in order to make or keep the system stable. But for transient, the large sort of oscillation of all rotating machines has been takes place. And in order to damp out that oscillation, the time period required, as well as in equal area criteria you studied the area under accelerating region and deaccelerating region. So that should be matched, then and then the system will maintain the stability. So that transient stability limit is less for the given power system. Obviously, in view of keeping this synchronous operation under steady state as well as the transient, the power angle curve has been utilized. That is P versus delta curve. This is delta versus P curve. And obviously, the peak of this curve is called as the maximum power handling capacity P max, which is equal to what? The magnitude of sending end voltage into magnitude of receiving end voltage divided by reactance of a transmission line. So from this power angle curve, we come to know that your power varies with the delta positively for load angle delta in between 0 to pi by 2. Whereas from pi by 2 to pi, that is 90 to 180 degree, that P versus delta relation is negative. Means with the increase in the delta, electrical output goes on decreasing. So particular transmission line, if you want to transfer maximum power, then it has to operate for delta is equal to pi by 2. But under that circumstances, for small variation in the load, if suppose small increase in the load happens, your delta will increase, and with that increase in the delta, you will come to know that your P will decrease. And because of that increased demand has to fulfill by increasing the generation. But here, because of that increased demand, there is a decrease in the generation, and that difference between the demand and generation mismatch increase, and it will further increase the delta. It will further decrease the P, and in that way the system will collapse. That is why the system has been operated under such a load angle delta, such that if any sort of changes in the load happen, it will be able to regulate by maintaining the synchronism. So this is the, we can say, the loading condition, the electrical output which is delivered by the machine at an load angle delta. Now under these circumstances, if any sort of variation in the load happen, so according to that, delta will increase, and accordingly the P delivered by the machine will increase. If the load is decreased, accordingly the electrical output of the machine will be decreased by reducing the delta. So that is possible. So that's why the operating angle delta, in view of keeping that steady state operation in mind, can be operated less than delta is equal to 90 degree. But if very large disturbance has to sustain, then the stability margin you need to keep a large, and for that reason the operating angle delta were kept in the range of 30 to 40 degree only, so that if any large transient takes place, that machine will still able to maintain the synchronism with each others. So that is governed by your transient stability. Another term is there, that is dynamic stability. Basically, this dynamic stability is nothing but the ability of the power system to remain in synchronism for small variation in the load only. But the difference is that with the steady state stability is that the dynamic behavior of the automatic voltage regulator and the governor, which is there with the synchronous machine as an auxiliary devices, is considered. Means as there is any load variation takes place, the governor will sense that and accordingly it will regulate the mechanical input to the generator. If there is any reactive power variation in the load happens, that automatic voltage regulator will accordingly sense the voltage and regulate the excitation of the synchronous machine. So if the effect of that automatic voltage regulator and the governor has been considered while analyzing the steady state stability of the power system, then it is called as the dynamic stability. So this is about the steady state stability, dynamic stability, and the transient stability of the power system. Next one is the voltage collapse. That is, sorry, frequency collapse. Here, as we know, the generator of some rating, suppose 500 kilowatt, can be load up to 5 kilowatt only. If it is loaded further, what happen? It will slow down and accordingly the frequency of generated power by that generator will be reduced. Obviously, 500, when 5 kilowatt generator we are talking about, it's not mean that if it is operated on 5.1 kilowatt, it will drop a frequency lot. It will not so. It can have some overload capacity. Means that 5 kilowatt generator, if we are loading for some 7 kilowatt or 8 kilowatt, then in that case, what happen? The drop in frequency will be very large. And because of that, that generator will suddenly stop. It is like that if we are having an capacity to carry a 5 kg weight on our head and to walk with normal speed. So if we carry some 6 kg load, then we can carry it, but with some reduced speed. 7 kg we can carry, but with very reduced weight speed we can say. But if suppose further increase in the load on our head happens, automatically we can not able to walk. So like that the machine is there. If we load it to around its rating, then it can carry it without any problem. But if it is loaded more, then it will suddenly stop running because of that overload and the system will collapse. So that is basically called as the frequency collapse. So here frequency term is in relation with the real power loading of that particular generator we are talking about or the power system we are talking about. So if there is a very large mismatch between real power generation and the real power demand, then under that circumstances, the system will collapse due to the under frequency. That is called as the frequency collapse. Similar is the term for voltage collapse. That is, if the reactive power load on the power system is greater than the reactive power generation, then in that case the system voltage will be affected. And the under voltage relays, like they are having a duty to check that whether the balance has been made between the reactive power generation and reactive power demand simply by sensing the voltage, whether the voltage is rated or not. If it is going below the rated, it seems that the reactive power demand is greater than the reactive power generation, and because of that, your system frequency drops, and according to that, the voltage dependent load will reduce their power consumption and match with the generation. That is an automatic, we can say, interdependent happening in the operation of the power system. But if that mismatch is very large, if we draw the curve for like system voltage with the reactive power consumption by the load, then it should be flat. Means with the increase in the reactive power demand, that voltage variation should be zero. But it is not happening so. It is like that because of reactive power demand, the voltage is goes on reducing. And at some particular knee point, that increase in the reactive power demand suddenly drop the voltage to zero. That is what called as the voltage collapse. And because of
Sir,
that, the system will. Hello,
screen is not visible.
screen is not visible.
I think you left the meeting
No, no. I am there actually, but I think
on the laptop.
this. No, no. On desktop, that net issue comes. I don't know what is the problem. My desktop, that audio is not working. That's why I am logging through mobile. So that is working, but internet issue is there. Just minute. Yeah, net issue has arise on the desktop. Okay, anyway, I will try to share with my mobile screen. Now, is the mobile screen is visible?
Yes, sir.
Yeah, so we were talking about that voltage collapse. So here, because of mismatch between the reactive power generation and demand, that chances of voltage collapse increase. How much mismatch is there, that is going to decide that whether the system will sustain it or will collapse. 2 3 year back, I think three year back, you might be heard that almost for 8 to 10 hours there was a blackout in western region of our India, and that was because of overdrawn by UP Electricity Board. You might be heard that. So that is happens because of frequency collapse. Means one of the utility has consume a use power from the national grid, and because of that, what happened? The frequency droops suddenly, and the under frequency relays as a protective devices in the operation of that grid will operate sequentially, and because of that the loads get disconnected and the whole region becomes blackout. So that is what the frequency collapse basically, example of frequency collapse. So here, this frequency collapse and voltage collapse can be avoided always by regulating the operation of the power system according to the loads on it actually. And that is has been taken care by your automatic voltage regulator and governor. Governor takes care for real power match, and AVR takes for automatic voltage regulator. But obviously, it is according to the ratings of the machine. Means if machine is already excited to full and till further increase in the reactive power demand has happened. So it is not get regulated. So under that circumstances, you need to have some other options to balance that reactive power demand. Or whatever reactive power sources you have been adopted in your power system should be according to the previous scenario or operating requirements of that power system. You need to plan that. The last one, that is the subsynchronous resonance. Here you might be heard about the resonance. In electrical circuit, you heard the resonance if there is a L and C in series resonance that we usually called it. If the inductance and capacitor is connected in series, so for rated fundamental frequency, that inductor will offer inductive reactance XL and capacitor will offer capacitive reactance XC. But if that electrical LC circuit is energized by some voltage source, which is having some another frequency component also along with fundamental. So for that another frequency component, they also offer some another inductive reactance according to that frequency 2 pi f of that component into L. Similarly, XC, that is 1 upon 2 f of that component into C. And for that frequency, if that XL and XC of that frequency matches, so because of that, what happened, that XL become XC equal, and that circuit path impedance becomes 0 because XL is equal to XC, and because of that XL minus XC becomes 0. So that circuit path impedance becomes 0, and because of that, the large current of that frequency component will flow through that circuit. That is what we call it as a electrical resonance. So here, similarly, resonance will be takes place for a frequency less than the fundamental frequency. Now, as we know that generator and electrical network, it is some mechanical plus electrical system, means steam turbine driving the shaft of generator. Again, in steam turbine, there are 2-3 stages of steam injection on that shaft: low pressure, high pressure, medium pressure. So same shaft is under the stress of different level forces, and because of that, even though that shaft is running at a particular speed, but there is a oscillation of that shaft because of it expressed by different pressure at different location on that shaft, and that oscillation is of small frequency. If that oscillation of small frequency driving that generator, means what, generator आपका rated speed पे भी घूम रहा है, along with that some oscillating rotation of that shaft is also happening. So because of that, whatever power gets generated into the electrical armature winding of that generator, it is of that fundamental frequency along with that of oscillating speed का जो frequency रहेगा उससे related frequency, वो frequency का component of EMF is also induced into the winding of that synchronous machine. And now when that generator winding is connected to the transmission line, और ट्रांसमिशन लाइन के भी पैरामीटर है, ELC पैरामीटर्स है एंड दैट ऑल, उसमें अगर वो इलेक्ट्रिकल सर्किट में वो पर्टिकुलर मोड ऑफ फ्रीक्वेंसी जो है ऑसिलेटिंग, वही फ्रीक्वेंसी के लिए अगर इलेक्ट्रिकल सर्किट का एल एंड सी कॉम्पोनेंट जो है वो भी अगर रेजोनेंस क्रिएट कर देते हैं, व्हाट हैपन, दैट मोड विल बी गेट एनर्जाइज एंड दैट मोड बिकम more excited than the fundamental frequency mode, and because of that the whole turbo generator setup will break the foundation for that, means that oscillating mode will be get energized lot, and because of that that turbo generator setup will come out of foundation, like that problem may takes place. So why it is called as subsynchronous? Because it is at the frequency less than the fundamental frequency, subsystem, sub frequency. That is subsynchronous. You know, for synchronous speed, the frequency is fundamental. So for speed less than synchronous speed, the frequency is less than fundamental. So subsynchronous resonance it is called, because it happens at frequency less than the fundamental frequency. So here, the factors which limits the loading capability of the means actual loading of a transmission line is limited by three factors. One is thermal rating, means we can say the power rating of a transmission line. Up to that only we can load it, which is obviously depends on the environmental atmospheric conditions. According to that, that rating is varying. Second one is the dielectric rating of a line, that is operating voltage level rating of a line. And third one is the stability issues. Means we load the lines such that this stability problems will be avoided. So according to that, only the line can be loaded. So this is what about the loading of a transmission line. Then the next point, that is now for discussing this next point, I should just a minute. I need to take some. Is the screen, mobile screen is visible? No?
Yes, sir.
Yes, sir.
Because it is not open. To open with. Yeah, the next point is power flow and dynamic stability consideration of interconnected transmission system. So this we already discussed in power system 3 also, that how the power flows through a transmission line which is interconnecting two regions. Here suppose one region having its total generation and demand, and the another region having its generation and demand, and there is an exchange of power between these two regions through the transmission line which is connecting these two regions having an reactance X. Now the power flow through this transmission line, has been given by what? Magnitude of voltage E1, magnitude of voltage E2 divided by X into sine of delta. That is what we already derived. In power system 3. Now here, in this, how the P and Q is the function of voltages at both the end, their angles and X, that is we know. But I think you are from B division, na? Yeah, okay, no problem. A division में simulation lab में I will going to explain that how. Anyway, what I want to say that power flow through this transmission line is given by the expression. It is given by the expression which we know very well, that magnitude of E1 into magnitude of E2 divided by X into sine of delta. Here graphically it is derived, but analytically we already derived in power system 3. Now what we come to know कि जो लाइन में से पावर फ्लो हो रहा है वो डिपेंड करेगा कि भाई E1 कितना है, E2 कितना है, X कितना है एंड डेल्टा कितना है. बट एक्चुअल प्रैक्टिकली होता अलग है. होता क्या है कि रीजन 1 में how much real power generation is going on, how much demand is there, according to that remaining it will inject into the transmission line. Same cases happen at the another end. Another end पे क्या होता है कि how much real power generation is going on, how much real power demand is there in that region, according to that the power either get injected into the transmission line or may be drawn from the transmission line, and in that way the whole generation in both the region and whole demand in both the region is balanced, and for that balance there is some system frequency F which is same in both the region. In that way the system get operated. Now how power get injected into the line or drawn from the line either at the region end 1 end or region 2 end, according to that the voltages and the angles will be get developed at the end of the transmission line. So here what they consider P1 means the power which is injected by region 1 into the transmission line. P1 is the power which is get injected by the region 1 into the transmission line. Now if we talk about the transmission line, it is only considered the inductive reactance. So there is no real power loss into the transmission line. So because of that, whatever power injected by region 1 into the transmission line, the same power will be get drawn by region 2 from the transmission line. But if the definition for P1 and P2 is same, मतलब P1 का definition अगर मैं बोलूँगा real power injected by region 1 into the transmission line, what given U1 E2 divided by X into sin of delta. P2 का भी अगर मैं definition बोलूँगा कि real power injected by region 2 into the transmission line अगर मैं बोलूँगा, तो what happen? It is basically negative. It is not injecting, it is drawing that power, and which is same as that of what injected by region 1 into the transmission line. So in that case, P1 is equal to minus of P2. If definition for P1 and P2 is different, P1 का definition मैंने क्या बोला? Real power injected by region 1 into the transmission line. और P2 का definition मैंने बोला real power injected by region 2 into the transmission line. अगर ऐसा definition है तो P1 is equal to minus of P2. लेकिन P1 का definition as it is, real power injected by region 1 into the transmission line, and P2 का definition अगर मैं बोलूँगा real power injected by transmission line into region 2 अगर मैं बोलूँगा, तो in that case that P1 is equal to P2. P1 is equal to P2. Hope you are understanding what I am saying. Because that P1 and P2 both are same in magnitude. Only the one is injecting and another reason is absorbing. So that's why it is negative. अगर हमने P1 P2 का definition दोनों के साथ same ही रखा तो injected by region into the line अगर हमने ऐसा definition रखा both P1 P2 के लिए, तो वो केस में P1 is equal to minus of P2 आएगा. लेकिन definition अगर आपने change किया, P1 के लिए मैंने बोलूँगा real power injected by region 1 into the line, लेकिन P2 के लिए मैं बोलूँगा real power injected by transmission line into the region 2, तो वो केस में P1 is equal to P2. And it will be same as the transmission line is lossless, which is equal to E1 into E2 divided by X into sine of delta. That is same for P1 as well as P2. So as per this, the definition is what? P1 का definition अलग है, P2 का अलग है. Please try to understand. P1 का definition है power injected by region 1 into line, और P2 का definition है power injected by line into region 2. Same expression will be, similar expression will be there for reactive power injected by region 1 into the transmission line. That is equal to what? Magnitude of E1 square divided by X minus magnitude of E1 E2 divided by X into cos of delta. Whereas the reactive power injected by region 2 into the transmission line, reactive power injected by region 2 into the transmission line, same definition अगर मैं बोलूँगा तो Q2 is equal to E2 square by X minus E1 E2 by X into cos of delta. Whereas for P1 P2 is same as there is no losses into the transmission line. So P1 is equal to P2 is equal to P is equal to so. As per this equation, I was already told you that if we want to control the power flow through the transmission line, that can be controlled either by E, by controlling magnitude of E1, or by magnitude of E2, or by delta. Now how it can be done, that is what again explain here graphically. Here what they did, they just draw one phasor diagram. For this two machine system, let's say E2 at an angle of delta 2 is the reference bus. With reference to that, E1 at an angle of delta 1 phasor has been drawn, and the difference between this E1 and E2 is nothing but the voltage drop across the transmission line, that is EL. As the transmission line is inductive only, there is no resistance. So whatever current will flow through the transmission line, will be in quadrature with the voltage drop across the transmission line. EL के quadrature में I रहेगा because that circuit is only inductive in nature. So according to that, if we draw the current phasor I perpendicular to your EL phasor, ये EL का phasor है आपका, Perpendicular to that is the phasor for I. So in this way, the phasor diagram, in this way, the phasor diagram for this two machine system has been drawn. Now, in view of controlling the parameter, if we go with this, as we all know, the power angle curve, P delta curve is there for a given power system, which is P is equal to E1 E2 divided by X into sine of delta. Now, by controlling this X, अगर मैं X को कम कर पाता हूँ by mean of some capacitor connected in series with the transmission line, I mean by compensating the series impedance of a line or series inductive reactance of a line. So I am going to change the height of this power angle curve. Means I am going to change the maximum power handling capacity of the line by reducing the X. Means X अगर मैं कम करूंगा तो I will increase the maximum power handling capacity accordingly. But obviously, when we will do this, when the actual loading of a line comes very less than the thermal rating of a line. That is what we explained in the last lecture, that in a mesh network, when this line is having a rating of 2000 megawatt capacity, but it load get only 1400 megawatt. Whereas this line is of rating of 1250 megawatt capacity, but get loaded for 1600 megawatt, means this line becomes overloaded. In order to avoid this overload, the power we need to divert through the another transmission line. But for that diversion, the whatever reactances offered by them are the hurdle. So what we did, we added the capacitor in series with the line here, such that the net reactance of this line will reduce, means power angle curve of this line will change. And for that given loading condition, we transfer the 1750 megawatt power through this line. Whereas earlier only 1400 megawatt flows. मतलब क्या किया मैंने, लाइन का रिएक्टेंस चेंज करके I will increase the loading of that line. But obviously this loading I will do if it is underloaded. ऐसा नहीं कि ये ऑलरेडी 2000 मेगावाट कैरी कर रहा है और इसके ऊपर मुझे लोडिंग बढ़ाना है तो मैं एक्स के साथ खेल के वो कर सकता हूँ. नो, बिकॉज इट विल गोइंग टू क्रॉस द थर्मल लोडिंग ऑफ अ लाइन. सो थर्मल लोडिंग के बियॉन्ड में जा नहीं सकता हूँ. एक्चुअल लोडिंग अगर मेरे पास लाइट हो रहा है और मेरे पास स्कोप है कि रेटिंग उसका ज्यादा है लाइन का, तो वो एडजस्ट करने के लिए मैं लाइन का रिएक्टेंस के साथ खेल के वो कर सकता हूँ. सो दैट इज व्हाट ग्राफिकली एक्सप्लेन हियर, दैट how we modify the power angle curve of a given line by modifying its reactance so that we can increase the power flow through a transmission line for the given condition. Given condition matlab, let's say this is the operating condition. So P flowing through line and delta according to this line was this. Now I come to know that for this delta exists, the power flow P0 is 1400 megawatt, whereas the line is having a capacity 2000 megawatt. So what I will do, I will reduce the X. So the same delta के लिए, this much power I can able to transfer through the same transmission line. But when it is less than the thermal rating of the line, thermal rating आपका बहुत ज़्यादा है और actual loading कम हो रहा है, तो वो हमको utilize करने के लिए we can do that. So this is how with the playing with the X we can do that. Second one, as I said, X के साथ हो गया. Magnitude of E. Please stick to this equation. Okay, how we are playing with X delta E1 E2. Now here we have this earlier curve E1 E2, its difference EL, and according to that the current is this. Now if at any one end of the line, suppose end 1 के लिए I will add up some shunt compensator like voltage regulator and I will change the magnitude of that E1 bus voltage. मैंने वो लाइन का E1 end का bus 1 end का voltage का magnitude मैंने बढ़ा दिया. Now with this increase in the voltage, what happened? The difference between E1 and E2 चेंज होता है, बट उस मैग्नीट्यूड चेंज इज वेरी स्लाइट. यहाँ पे ये मैग्नीट्यूड देखेंगे और ये मैग्नीट्यूड देखेंगे तो स्लाइट चेंज इन द मैग्नीट्यूड इज देयर बिटवीन द वोल्टेज ड्रॉप अक्रॉस द ट्रांसमिशन लाइन. Whereas angle of EL change significantly. Angle of that voltage drop across the line, that is E1 minus E2, change significantly. So because of this, what happened? As we know, the current flowing through the line is in quadrature with the voltage drop across the line. So ये EL का फेज चेंज होने की वजह से क्या होगा, आपका I का भी change in the magnitude is slight, but the change in the phase angle of that I is significant. And as there is a change in the phase angle of I is significant, it is causing a change in the reactive power flow through the line significantly. So in short, by changing the magnitude of any one end voltage of a line, it is possible for us to significantly change the reactive power flow through the line, whereas the real power flow through the line is less significantly changed. But if rather than ending the change in the voltage at the end of the line, if we change the voltage drop across the transmission line without changing the end voltages, end voltage I will keep as it is, but I am injecting some voltage in series with the transmission line such that it will be in phase with the voltage drop across the transmission. इतना magnitude of voltage मैंने inject किया in series with the line, which is in phase with the voltage drop across the transmission line. So because of this, what happened? The change in the magnitude of current, पहला current ये था, quadrature to this because phase is as it is. So in addition to that, some additional current will flow through the line. Now here, change in the magnitude of current is significant. Phase angle is as it is. This cause and significant change in the active power flow through the transmission line. This cause significant change in the active power flow through the transmission line. So please keep in mind, अगर मैं end का voltage का magnitude change करता हूँ, तो it is causing a significant change in the reactive power flow through the transmission line. If I am changing the voltage drop across the transmission line, उसका phase angle as it is रखता हूँ, खाली magnitude बढ़ाता हूँ, तो it is significantly changing the real power flow through the transmission line. And obviously in between, if suppose I inject the voltage such that I can able to make it either in phase with the end voltage or in phase with the driving voltage. Any phase relationship में अगर मैं control कर सकता हूँ, means I can connect one voltage source in series with the transmission line. By mean of that, I am injecting the voltage in any phase angle 360 degree. That may be in phase with the end voltage, that may be in phase with the voltage drop across the transmission line, or any other phase angle. If I make according to that make in the phase angle, there is a control in either I will control the magnitude of current, phase angle of current flowing through the line, and according to that I am able to control both real and reactive power flow through the transmission line. So you please keep in mind that as per this equation, graphically we discussed that if we change the x of a transmission line, we change the power angle curve of a line, and accordingly we change the loading of that transmission line. If we change the magnitude of E1 or magnitude of E2, it will help to change the reactive power flow through the transmission line significantly. If we change the voltage drop across the transmission line magnitude, then it will significantly change the real power flow through the transmission line. And the combination of this we can use according to our need of loading the transmission line. The combination of this we can do according to the need of our loading the transmission. And obviously as we change the voltage drop across the transmission line, then accordingly it change the phase angle difference between the end voltages of a transmission line, that is delta, and that cause the significant change in the real power flow through the transmission line. So here this is how in a two machine interconnected system, the power flow through the transmission line is controllable by mean of either providing some series compensator or shunt compensator, or by compensating the line reactance. Obviously that we will see in details in a coming lectures. So, sorry. So for today we stop here. You please mark your attendance. Okay, please mark your attendance. Those who mark can leave the meeting.